Hello everyone, my name is Tianyu. I'm from the Institute of Information Engineering and University of Chinese Academy of Sciences. The paper I will be presenting today is titled SiamHAN, IPv6 Address Correlation Attacks on TLS Encrypted Traffic via Siamese Heterogeneous Graph Attention Network. Over the past years, we have witnessed an increasing number of network providers expediting the deployment of IPv6. Due to these efforts, 1/3 of Internet users can now access online services through IPv6. With this growth in use, however, come increased focus on security and privacy issues. A particular concern for the privacy of IPv6 users is the user activity correlation attack. In this attack, which works even on traffic encrypted by transport layer security, an adversary could leverage traffic meta information to identify and track users. Unlike IPv4 addresses, which are typically masked by a network address translation, an IPv6 address rarely corresponds to one single user. Therefore, a correlation attack against IPv6 remains a serious individual-level privacy threat. The attack can be grouped into two categories. Address-based correlation allows an adversary to associate an IPv6 address with the user's activity. For example, tracking the constant interface identifier in the address format. To eliminate this issue, RFC 4941 standard proposed temporary addresses, which implement frequently changed pseudo-random interface identifiers to counter this threat. Traffic characteristic correlation associates traffic with users' activities by analyzing the patterns in the encrypted traffic. However, existing technicals can only correlate the traffic of a closed-word dataset. Unknown users are still difficult to identify. Currently, IPv6 user traffic consists of frequently changing client addresses and widespread TLS payload encryption, which renders correlating IPv6 users completely invisible. That's a great challenge for the adversary to perform activity correlation. In this paper, we demonstrate that a more sophisticated approach could overcome this limitation. We introduce an IPv6 address correlation attack, which learns a correlation function from TLS encrypted traffic. Using the function, an adversary could determine whether two arbitrary addresses belong to the same user. The attack includes two steps: building knowledge graphs and learning the attack model. In the attack scenario, the adversary could wiretap the traffic of C client addresses from n IPv6 users on an observation point. The relationship between users and addresses cannot be detected due to TLS encryption. Based on the background knowledge of the encrypted communication of all IPv6 addresses for a wiretyping time t, the adversary could judge the relationship of a pair of addresses through a correlation function f. The function can be learned by an attack model providing the distance metric with a threshold eta. To obtain the ground truth dataset, we could use leaked plain text cookies to help train the attack model. Although the user data is protected by TLS encryption most of the time, a few users expose their HTTP plaintext since they use the changing addresses and access some websites without HTTPS deployment. Then the adversary could easily label these addresses by using the plaintext cookies. Once obtaining the model, the adversary could perform large-scale correlation attacks on the wide TLS traffic without plaintext. Our attack model is named SiamHAN, which contains two steps to perform the attack. First, we use heterogeneous graphs to build the knowledge graph for each address. Each graph contains three types of nodes: The client node C is the IPv6 client address. The server node S is the IPv6 server addresses who have established TLS communications with the client. The fingerprint nodes are field values of the client hello, server hello, certificate messages, and the statistical characteristics of the TLS connection, which includes client fingerprints and server fingerprints. Then there are also three types of metapaths to connect these nodes. The SCS metapath connects S and C, which represents the TLS connection activities between the client and the multiple servers. The FCF metapath connects C and the client fingerprint F, which represents the browser parameters that may be used behind the client. The FSF metapath connects S and the server fingerprint F, which denotes the service characteristics behind each server. Second, we propose Siamese heterogeneous graph attention network to build the attack model. The model inputs the knowledge graphs of two arbitrary client addresses. Then the multi-level attention mechanism matches the similar features between the two heterogeneous graphs to learn their graph embeddings. Finally, the model measures the distance of the embeddings to judge the correlation relationship. The architecture could be divided into four objectives. Node-level attention learns the importance of metapath-based neighbors and aggregating them to get the thematic specific node embeddings. The high attention value means locally matching the similar node attributes between the two graphs. Thematic level attention aggregates these thematic specific embeddings to get comprehensive node embeddings for each node. Finally, graph level attention aggregates all node embeddings to get the graph embeddings by globally matching the similar nodes. In the end, the model measures the distance between the two graphs and judges the correlation relationship between a threshold through a threshold. The model training is guided by the contrastive loss function. After obtaining the pre-trained attack model, the IPv6 address correlation attack could be applied to long-term user tracking task. In the task, the adversary knows one client address activity of each target users. Then she could compute the relationship between each target address and each test address to perform user tracking during the observation. User discovery is the second challenging task applied by SiamHAN, which could obtain the address groups to discover unique IPv6 users. To obtain the true number of users behind the TLS traffic in each iteration, we calculate the average distance between the new input address and each determined user group's addresses. If the distance is larger than a threshold, we create a new user group for the new address, otherwise classify it to the group with the closest distance. We passively monitor the IPv6 user traffic from March to July 2018 on China Science and Technology Network. Following the collection ethics, we finally obtained 1,700 users by using the labeling trick with persistent cookies. To simulate a realistic sighting implemented by an adversary, we evaluate SiamHAN with a time-based split on the 5-month dataset in most experiments of the paper. The baselines of the paper include user IP profiling, user SNI profiling, client fingerprinting, and deep call, which perform user correlation from dimensions including user profiling, TLS fingerprinting, and the flow sequences. Our evaluation metrics include true positive read, false positive read, area under ROC curve, and accuracy. First, we show a case of multi-level attention visualization. In the node level and the graph level attention, the high attention values are led by matching the similar node attributes between the two graphs, like using the same fingerprints. In the semantic level attention, we could see that user browser parameters contribute more to the correlation learning. Combined with the analysis of graph level attention, the client meta information is more important than the server meta information in the correlation task. As a first look at the correlation performance, we evaluate SiamHAN's performance on the input of arbitrary pairwise advice. As can be seen, SiamHAN significantly outperforms the peer correlation algorithms with a wide gap. In addition, when evaluating on the different time gaps between training and test, the results indicate that SiamHAN's performance does not degrade obviously, demonstrating that the SiamHAN could conduct a long-term reliable performance. For the tasks of user tracking and user discovery, the state-of-the-art technicals could achieve only 85% and 60% accuracy, respectively. However, SiamHAN achieves 99% and 88% accuracy, which comes from SiamHAN's more hit than deep core. Here is our conclusion. In this work, we explore the implementation of user activity correlation on IPv6 networks. We propose IPv6 address correlation attacks, which leverage an attack model SiamHAN to learn the correlation relationship between two arbitrary IPv6 addresses based on the background knowledge of TLS traffic. We hope that our work demonstrates the serious threat of IPv6 address correlation attacks and calls for effective countermeasures deployed by the IPv6 community. That's all. Thanks for your listening. Thank you.